Hello. Today I'm going to talk about some research that we've been doing at the Advanced Propulsion Power Lab at Virginia Tech. We are working on the response of a lean direct injection to thermoacoustic instabilities, and I'll explain what that means in a minute. Lean direct injection is a novel type of combustion system that was proposed by NASA for the aerospace industry. If you look at the bottom right figure on your screen, this is an example of a typical combustor in a jet engine today. We have a very rich burning area, which means it's burning with a lot of fuel. And then we inject cool air and reduce the fuel air mixture as we burn. And the reason we do this is that we get very stable, robust combustion. But the downside is in this hot burning area here, we produce a lot of NOx, and that's not good for the environment. And also, there's some trade-offs with efficiency with this system. Lean direct injection was proposed by NASA Glenn, actually, and this figure in the middle of the screen is a schematic of it. Instead of bringing in dilution air, we put all the air and fuel together and mix it before we let it burn. In addition to this being better for the environment, it allows a shorter combustor length, which is very advantageous for military type applications. The problem with the LDI system is that it's very prone to combustion instabilities. Now, a combustion instability can be thought of as a resonance in a pipe, or a resonance you might have experience with everyday resonance in a Coke bottle if you blow over the top of the throat. Now, imagine that harmonic occurring when there's combustion going on, and we find that the pressure waves amplify significantly. And these can get extremely violent and extremely loud, and it can damage the combustor, and it's not feasible to operate in these unstable operating conditions. Unfortunately, LDI is very susceptible to these, whereas current engine designs are less susceptible. What we want to do is we want to try to understand some of the mechanisms that cause these instabilities to manifest so that future designers can work to design a lean direct injection system that is not prone to these instabilities. For our purposes, we're going to do this by studying the droplets that come out of the injector as they burn. We want to do this because we know that heat release is very important to instability formation, and we know that droplet sizes is very influential on heat release. We've designed a combustor at the APPL, and it's an atmospheric pressure combustor. And you can see this schematic and image on the top right corner. We have a dynamic pressure transducer to measure the acoustic fluctuations, and as well as several microphones. And we have these flattened windows, and we'll see why these are important in a minute. Droplet measurements in a flow field can be very challenging. A device called a phase Doppler particle analyzer, or PDPA, is one of the only ways to get a non-intrusive droplet size measurement. In essence, the PDPA has two laser beams that you can see in this cartoon on the top right, and the interference between the two beams causes light and dark fringes, and as the droplet travels through, it scatters the light. On the bottom left corner, you can see a schematic of the PDPA system, and this is why we need windows that are flat and clear so that we can shine the laser beam through. In the bottom corner here, you see the measurement plane, and we're going to take the PDPA and we're going to measure droplets at 35 locations along this plane to get a feel for the spatial variation of the phenomena that we're measuring. Here are some time average results. These are solder mean diameters. This means that we sit at each one of these locations and we measure droplets for several seconds. The plot to visualize these has position on the X and Y axes, and this corresponds to the measurement plane that you saw in the previous slide. The relative size of the marker is an indicator of the size of droplets that we found at that location. And the blue corresponds to stable operation, and whereas the green corresponds to unstable operation. So for example, we see that at a location of 11 millimeters, 10 millimeters, we saw unstable running had 125 micrometers, whereas at the stable condition, it was 63 micrometers. We see from this plot that the instability does significantly change the droplet sizes throughout the flow field. In fact, it changed all of them except for two, which were relatively the same between stable and unstable operation. This has been done before. Can be seen in the literature. We already know that acoustics affect sprays. So the next thing we want to do is look at the fluctuation frequency. So the hypothesis that we're looking at is that during an instability, we want to know if we will see droplet diameter fluctuations at the instability frequency. The reason that we're looking for this response is because fluctuations in heat release at the instability frequency can either damp or excite an instability. And we want to know if the droplet might be a coupling mechanism for an instability formation. If you see the power spectrum in the bottom right corner, we are plotting two different FFTs, one for a stable condition in red, and then one for the unstable behind it. And you can clearly see that there is a peak at 400 hertz in the unstable case that is not there in the stable case. This is remarkable because not only are we seeing a frequency of fluctuation for the droplets, but it also is at the frequency of instability, which we can confirm by looking at the FFT of the pressure signal during the instability, which is also right at 400 hertz. And the next steps would be to try to relate droplet sizes to heat release rates and try to use this information to understand whether the droplets are a fundamental coupling mechanism or is it just something that occurs after the instability has already manifested. Thank you for your time.